Hello everybody, welcome to Guidancee Education channel. We will see the topic that is discussed in this video. We are continuing class 11 physics, motion in straight line. In this video, we will discuss Galileo's law of odd numbers. We will see the statement, explanation and proof. I will also explain the shape of the position time graph for a freely falling body in the light of Galileo's law of odd numbers. This video will be a little long, but do not skip the video. Watch the video completely so that you get all points clear. And if you think the video is useful, do like the video, share the video with your friends, and also leave your feedbacks as comments in the comment box below. If you have not yet subscribed my channel, do subscribe my channel and support me. Also press the bell button and all button for notification of more videos like this. Thank you very much for your support. Come, let us start the class. The topic is Galileo's law of odd numbers. We will first state the law, see the explanation, and then go on to prove the law. Finally, I will also explain the shape of the position time graph in the case of an object falling freely from rest. Galileo's law of odd numbers is given as part of free fall in your syllabus, but in reality, it is applicable to objects moving with uniform acceleration starting from rest and moving in a straight line. Watch the video completely without skipping so that you understand all points clearly. This concept will help you solve even difficult problems associated with this. Now let us see the statement. The law states that the distance traveled by a freely falling body during equal intervals of time stand to one another in the same ratio as odd numbers beginning with unity. That is, in the series of odd number, the first number should be equal to 1. That is, the ratio of the distance traveled will be 1 is to 3 is to 5 is to 7 is to and so on. That is, if we consider the equal intervals of time as equal to 1 second, then the distance traveled during each second will bear to each other a ratio equal to 1 is to 3 is to 5 is to 7 is to and so on. That is, if during the first second it covers 1 unit of distance, then during the second it covers 3 units, in the third second 5 units, the fourth second 7 units and so on. Let us consider an object falling freely from a certain height above the ground. What is its initial velocity? Initial velocity u is equal to 0. It experiences an acceleration equal to negative g. Let us suppose it is approximately equal to 10 meter per second square. This is the initial position of the ball at a certain height from the surface of the earth. I have already posted a video on free fall. If you have not watched it yet, click the I button in order to watch that. I have discussed all the details there. We have to consider equal intervals of time. Now, for the present, we will consider that equal interval of time as equal to 1 second. During the course of its movement downward, let us suppose during the first second, it moves down by a distance equal to h1. During the next second, it moves down by a distance equal to h2. In the third second, it moves down by a distance equal to h3. And during the fourth second, it moves down by a distance equal to h4 and it is now resting on the ground. From the diagram, you can see that each second, that is each equal interval of time, the distance covered by the object is increasing. It is not the same distance. Galileo's law states that these distances bear to one another the ratio of odd numbers. In order to prove this law, we have to find out the values of h1, h2, h3, h4 and then compare them. For that, we have to develop this diagram a little bit and understand a few more points. During the first interval of time, let us suppose S1 is the displacement. We just use only the absolute value so that we can avoid the direction. Displacement is a vector quantity, S1. By the end of second, the displacement is equal to S2. Here also we use the absolute value. During the third second, the absolute value of displacement is equal to S3. The absolute value of displacement for the fourth second, that is the whole distance it has traveled, it is equal to S4. Now we will see how H1, H2, H3 and H4 is related to S1, S2, S3 and S4. From the diagram we can understand H1 is equal to S1. H2 will be equal to S2 minus S1. Again, these are all absolute values. Distance H3 will be equal to S3 minus S2. Distance H4 will be equal to S4 minus S3. All absolute values. Galileo's law states that H1 is to H2 is to H3 is to H4 is equal to 1 is to 3 is to 5 is to 7. That is the relation as is shown by the odd numbers. For this, we have to calculate S1, S2, S3 and S4. Total distance S traveled during the 4 seconds can be easily calculated using the formula S is equal to ut plus half a t square. Since u, the initial velocity, is equal to 0, this formula becomes S is equal to negative half gt square. Because a is equal to negative g. Substituting the values, we get S is equal to half 10 into 4 square. For the present, we are ignoring the negative sign. The negative sign suggests that it is moving downward. On simplification, this will become equal to 80 meter. But to calculate the distance traveled during each second, we have to use another formula. Now we will proceed to calculate values of S1, S2, S3 and S4 so that we can calculate H1, H2, H3 and H4. S1 is equal to ut plus half a t square. U is equal to 0, A is equal to negative g. Anyway, we are not considering this negative sign. We are only taking absolute values of S1, S2, S3 and S4. Since ut becomes 0, this equation becomes S1 is equal to half gt square. The absolute values of S1, S2, S3, S4 are not equal. And the time taken for this displacement also is not equal. To avoid confusion, we use another symbol for the time taken for the displacement is equal to S1, S2, S3 and S4. The symbol taken is T is equal to tau. So the time taken for S1 is tau, for S2 it is 2 tau, for S3 it is 3 tau and for S4 it is 4 tau. That is how the time is considered. I will mark these displacements in the diagram as tau, 2 tau, 3 tau and 4 tau. Absolute value of S1 now becomes half g tau square, which can be written as g by 2 tau square. Absolute value of S2 will be equal to g by 2 tau square. That will be equal to g by 2 4 tau square. Similarly, S3 will be equal to g by 2 3 tau square equal to g by 2 9 tau square. And lastly, S4 will be equal to g by 2 4 tau square equal to g by 2 16 tau square. Now that we have the values of S1, S2, S3 and S4, it is very easy to calculate H1, H2, H3 and H4. S4 is also absolute value. You have to put one line on either side. So H1 will be equal to S1 equal to G by 2 1 tau square. H2 is equal to S2 minus S1. That will be equal to G by 2 4 tau square minus G by 2 1 tau square equal to G by 2 3 tau square. We will carry it over here. H2 is equal to G by 2 3 tau square. H3 will be equal to S3 minus S2. That will be equal to G by 2 9 tau square minus G by 2 4 tau square. That will be equal to G by 2 5 tau square. We will carry it over here. H3 is equal to G by 2 5 tau square. Coming to H4, it will be equal to S4 minus S3 equal to G by 2 16 tau square minus G by 2 9 tau square. That will be equal to 16 minus 9 equal to 7 tau square. So G by 2 7 tau square. We will carry over the value here. H4 is equal to G by 2 7 tau square. The ratio of H1 is to H2 is to H3 is to H4 will be 1 is to 3 is to 5 is to 7. That is the same as the ratio of odd numbers. All the other quantities are the same, so they get cancelled. This is what Galileo's law of odd numbers state. We have proved that. Now let us see how we can find out the total displacement during a particular interval of time, say nth second. We have a separate formula for that. dn is equal to u plus g by 2 into 2n minus 1, where n is the time considered. This is the formula for calculating the distance travelled at the nth second. So d1, the distance travelled at the end of first second. U is equal to 0. G is approximately equal to 10. So 10 by 2 into 2 into 1 equal to 2 minus 1 equal to 1. So 10 by 2 into 1 becomes 5. So at the end of first second, it has travelled 5 meters. At the end of the second, that is d2, will be equal to 10 by 2 into 2 into 2 minus 1 equal to 3. So 5 into 3 becomes equal to 15 meters. At the end of second, d3, the total distance travelled is equal to 10 by 2 into 2 into 3 minus 1, that is equal to 5. So 5 into 5 becomes 25. Distance travelled during the fourth second, d4 is equal to again 10 by 2 into 2 into 4 minus 1, which is equal to 7. So 7 into 5 becomes 35. So the total distance becomes 5 plus 15 plus 25 plus 35 equal to 80 meters. So this is the value that we got initially. That is total distance travelled S is equal to 80 meters. So for each second, though it is moving with uniform acceleration, the distance covered is different. So the position time graph shows this difference. I will just explain that graph. I have already prepared the XY graph for freely falling body. Note the shape of the graph. D1, D2, D3, D4 are equivalent to H1, H2, H3 and H4. The total displacement for the first second is 5 meter. At the end of second, it is 15 plus 5 equal to 20 meter. Total distance travel for the first 3 seconds is equal to 20 plus 25 equal to 45 meter. The total distance travel for all the 4 seconds together is equal to 80 meter. You can notice here that the distance traveled during each second is not commensurate with the increase in the velocity during each second. That is why, though the shape of the velocity time graph is a straight line at an angle to time axis, this position time graph is a curved line. If you think the video was of use to you, Please like the video, share the video with your friends and leave your feedbacks as comments in the comment box below. If you have not yet subscribed my channel, do subscribe it now and support me. Press the bell button and all button for notification of more videos like this. Thank you very much. We will meet in the next video with another important topic like this. Till then, bye. Take care.